So the topic of the talk is going to be AI in supply chain management because, well, as you've seen, AI has literally taken off in the popular press. All you have to do is follow NVIDIA stock and understand that every CEO now wants to be involved somehow in AI, and every conference call has to have some AI component. McKinsey came out and showed this graph that in the for the past 6-7 years, AI has sort of been muddling through, and then suddenly OpenAI comes, generative AI shows up, and suddenly half of the companies that have never talked about AI, never adopted AI, have adopted AI. Gen AI has gone from 0 to 2/3 of the companies are using generative AI over the past 2 years. My conclusion from that is that as supply chain manager, we're going to be told that we have to use AI. We're going to be told, tell us how AI is going to make a big difference, a big impact on our company and on your supply chain management practices. And there are 3 ways to address that. Number 1 is ignore the question. Okay, that's not viable because you do have to answer to leadership. Number 2 is to take some machine learning model and say, well, here we're already using AI, and so we'll sort of be, and that's what probably most of the companies that were never adopted and become adopters have done. Number 3 is to say, I have a plan. And so I'm going to give you one plan, one program that you could consider as you come to management and say, here's what I'm going to do with AI. That requires a budget, that requires investing in resources and people and data, etc. And so my subtitle might be creating the business plan for digital twins in supply chain management, with a bold statement that this requires investment. Right? If you're told you have to build something, then build it, but do it correctly. And number 2, it has presumably an ROI, right? So I'll show you where that ROI might be. I'm not going to give you financials on digital twins, but I'm definitely going to show you where you can show that there will also be an ROI from the digital twin business case. So this might be my subtitle is sort of using digital twins in supply chain management, especially AI-based or AI-supported digital twins and giving you that the business case to show senior management. So you see, you've already gotten something out of today's meeting, today's presentations. So digital twins, and then my second subtitle is that digital twins are a way for the digital adopters to catch up with the digital natives. So the digital natives are the companies that were born after, 2000 or so, that they were already born into the era of the internet. So this is your Amazon and Netflix and Tesla and companies and the other electric vehicle manufacturers, and we have more car manufacturers in the last 20 years than we had in the previous 50 years or so come to be created. And so what about the digital adopters, those that were like me born before year 2000? How can we catch up? And so this is Siemens' approach. And Siemens basically said, what we're going to do is we're going to build a digital twin of a car, because we're going to build the foundation for a digital twin of a car, and then every car manufacturer or every car that wants to be created, we can now create that version or that model in our digital twin environment. And so through meticulous analysis of the car manufacturing, the car process, they went and built a one-to-one digital replica of an automobile, and through that they can now replicate many different types of cars. What do you do with that? As you think one of the previous slides showed, or that you can now experiment with, say, well, eventually self-driving cars, but before that, automatic braking, right? And under different weather conditions, we can now experiment with what sort of automatic braking do we want to implement. So we've now replicated the car in the digital environment. We have replicated the environment, right? The road conditions, if they're hilly, if they're bumpy, if the roads are asphalt, if they're gravel, if they're well-maintained or not well-maintained, right? So we've created or duplicated all of that in the digital environment. I guess this is the image. And now we can experiment with different automatic braking systems that we could implement. Obviously, in the physical world, if you experiment with automatic braking systems and you experiment for too much, you're going to have a lot of accidents. You're going to destroy a lot of cars. Very expensive, not really a great idea. But then in the digital environment, I can experiment endlessly. And I can see, at what speeds do I have to stop? Given speeds and given interactions with the environment, how do I stop and how do I implement automatic braking? How does that change if it's raining, if it's snowing? Maybe in very hot weather as well, there might be changes to that. How do I brake in such a way that if my passengers are not wearing a seatbelt, they don't find themselves inside the front windshield because I braked too quickly? And so we can experiment with all that in the digital environment and then make recommendations for self-driving or automatic braking and any other attribute that you want in the manufacturing process, in the implementation process. As you think of what I've just said, you're saying, well, what you're going to implement is an algorithm, right, or a set of algorithms under these terrain conditions, under these speeds, given that I've seen cars moving around me, especially if it's snowing and the cars moving around me are not actually driving at their ways they're supposed to, I would implement self-driving in a certain way. And so a lot of what's going to come from a digital twin, or one direction to take digital twins, is to build algorithms that will then be implemented in, if we're talking about a vehicle, right? All of these algorithms are implemented directly in the vehicle manufacturing and the vehicle intelligence. So that's sort of where the engineers have taken the digital twins. Why is this relevant to supply chain managers? Because digital twins are valuable when there is uncertainty. Now I've caught your attention, because if there wasn't uncertainty, you'd all be out of a job, right? That's all we deal with in supply chain management, is the uncertainty. Did the vendor actually ship the product they were supposed to? Did sales actually meet their sales targets? Are there changes in consumer behavior that we now have to take into account? Does the warehouse actually have the products that it's supposed to have? And so all we deal with in supply chain is really uncertainty. And so now you see that this is why it's relevant to us in supply chain management as we integrate many items. So I'll give you another example of sort of the value of a digital twin, again from more of the engineering side. We need, on the one hand, uncertainty, which we all know is our bread and butter, or the reason we actually go to work in the morning, or those that didn't come here, were probably because something showed up this morning that they said, oh, wait a minute, I got to deal with this. I can't go to the conference I was looking forward to. That is, the uncertainty of the lives that we live in supply chain. The other aspect is granular data. We're starting to see very high-resolution data from various environments. Internet of Things, RFID, ERP systems, multiple ERP systems, disparate ERP systems, but as we'll talk about in a bit. And so this is GE, another digital adopter, right? Definitely not a digital native, coming into the world of coming in and catching up with the digital natives. So GE builds wind farms and wind turbines and wind farms, and wind, as we all know, definitely is characterized by uncertainty. Uncertainty over the course of the day, over the course of an hour, over the course of the year. When building a wind turbine, you will also find that there are differences in wind speeds and wind shear and wind direction as you increase the height of the wind turbine. And all that can be measured, right? So we can measure wind speeds in real time. We can measure wind speeds across time, across altitude. For a wind turbine that might be 200 feet or 250 feet or 300 feet off the ground. And so as they measure all this, and so they have tremendous amounts of data, they can now build a digital twin for the wind turbine. And this has implications at 3 levels, right? First, at the design level, you have to ask yourself, at what height do I want the wind turbine? And so that's a decision you make once, and it's there for the length of the wind turbine and the renewable energy there. And so through digital twins, through simulation of the physical environment with what you can expect to be able to generate in terms of wind at different hours, at different hours, at different of the day, at different times of the year, you might decide on specific heights for that wind turbine in that area, because you might want to rely more on renewable energy, say, at night, because you have solar energy available during the day. Or you might want more energy. You might need more energy in the summer, because in the winter, you're using more air conditioning. In the winter, you're using more natural gas heating and heating environment. So those are sort of the first decisions at the planning stage. And then over time, you can have real-time information about changes in wind direction and wind strength throughout the year, and then simulate how that might impact increasing the marginal efficiency of your wind turbines. You can change the yaw, you can change the angles, you can change the responsiveness of the wind turbine to their environment. And this might be something that you do on a regular basis, let's say once every 2-3 months. And so, while you can't do that in real time, you can do that sort of in a scheduled way. And then from the simulation of the environment and the simulation of what your wind turbines can, the changes in how your wind turbine blades are adjusted, you can then generate a schedule for an algorithm, basically, to build you a schedule for how to change the direction and the angles of the wind turbine. And then finally, in real time, when you have forecasts, say, of very heavy winds, maybe you're worried about hurricanes, maybe you're worried about tornadoes, maybe you're worried about, maybe there are, so that might lead you to simulating and then developing solutions that are very one-off and sort of very short-term. Depending on the technology that you have and the ability to change the angles of wind turbines automatically, you could also start investing in very short-term changes, maybe even change the angles a bit during the day, between day and night, to capture a few more percentages of efficiency over the wind turbines. And so these are where the engineering side has gone with digital twins. Supply chain management has definitely embraced digital twins. I've got a couple here, and then we'll talk about one more as well. So first of all, in supply chain disruptions, hurricane season is upon us, and as many in the supply chain area have figured out, an issue to deal with. And we've now learned from several years of interacting with the environment that hurricanes are quite disruptive, tornadoes as well. There could be other stoppages, other disruptions, like a port strike that we narrowly averted about a month ago, et cetera. And so if we look at hurricanes, for example, there are digital twins come into play solving the one-off problem, right? So every hurricane is different. It's going to have a different impact on warehouses, manufacturing, houses, the magnitude of the magnitude of the issue. On the one hand, the people that are going to be impacted, who are they, where are they located, on the one hand. On the other hand, they're going to impact the responders. And so the responders come in various flavors. There's the government, the government responders, which are like FEMA and the National Guard, which will come out and help. But many companies have to respond to hurricanes as well. Most notably, those like Walmart and Procter and Gamble and Home Depot and others have been known to be very effective in their response. Some of it is just to bring aid to people. Fresh water after a hurricane is extremely valuable. Procter and Gamble prides itself in being able to bring cleaning supplies, because the first thing you need is, or maybe the second thing you need is building supplies after you have cleaning supplies after you have fresh water and food and water. You have to make sure that you can now clean and disinfect it and make sure that the area is, and that people have places to live. And Home Depot comes in and says, well, we also need building supplies. If the situation is this bad, obviously you're not going to be able to do a lot, but if it's a minor damage, then we have to come in quickly to give people building supplies as well. And so those companies have built digital twins to say, this is the track of the hurricane, where are our current supplies located, where do we have warehouses, where do we have transportation routes, where do we have vendors that can manufacture product. So first thing, we have to get out of the line of damage. And so where do we go so that we can come back? How do we work with our vendors, vendors? Where do we pre-position material to be able to quickly respond to the needs of the population after the hurricane? And then how do we get our products back? And so those that have effectively built digital twins now have recommendations based on that one-off scenario. The difference between, say, this and some of the earlier examples I gave was that this is a digital twin whose sole purpose is to solve just one problem, or one problem hopefully like every few years, which is solve this hurricane. And every solution is going to be different. I can't create an algorithm I can't create an algorithm to solve my hurricane response, but I will use my digital twin and see how my supply chain is mapped in order to simulate different solutions and find out which ones are most effective across the board. Industry 4.0 manufacturing has also adopted digital twins extensively. And these have gone into sort of two notable directions. One is looking at equipment and simulating the lifetime of equipment. For newer manufacturing equipment that's been around 10, 15, 20 years, we have pretty good data. We have usually embedded information collecting data through embedded devices, and then we transfer that and we can analyze that data. Some of the equipment, though, that we are still working with is 30, 40, 50 years old. They collect a lot of data, but capturing that data, getting that data out of the machine might be a Herculean task anyways. And so Industry 4.0 has basically gone and said, let's collect all this data, because one of the things we want to do is say predict time to failure. When will a machine fail? Which for the most part is a boring question, right? You have a machine, it's going to fail, and you will repair it, I guess. And things will go well. Other than, Murphy's Law says that when will that machine actually fail? It's exactly when you have peak manufacturing demand, peak needs for that equipment, because that's when it's under the most stress. That's when your repair personnel are under the most stress. That's when everybody is working really hard, and that's when your machines tend to fail more likely. And so by simulating high-stress environments, and we can't physically simulate high-stress environments, so we simulate high-stress environments in the digital environment, figure out which parts might be more likely to fail, and then we implement preventive maintenance in an accurate way based on our predictions. Building sort of on what was said in the wind turbine environment, another place we see digital twins is in production manufacturing, especially in batch processing, where environmental factors might have an impact on yield, and that might be a result of heat, humidity, pressure, how long the raw materials have been waiting and standing. We might have different responses within our manufacturing process. And so through data collection, forecasting, and then simulation, we can develop, again, algorithms for optimal usage of our manufacturing equipment. Another area that's not listed here has been in transportation and transportation routing. We have our Transcom friends here who have built digital twins, I imagine, of a large part of their infrastructure of traveling. Many years ago, UPS figured out that left turns were very expensive because you could sit at a left turn for 5 minutes, and for a small package delivery, that 5 minutes at $50 an hour of employee and material equipment cost is more than your entire profit on a small package delivery. Morris Cohn is here. When I was in Philadelphia, we also learned that in downtown Philadelphia, making a right turn is impossible in certain hours of the day because as you get to that turn, suddenly there's 1 million people crossing the street as well. And so there, the problem is not that you can't make a right turn, but it depends on the hour of the day, and it might depend on whether it's raining or not raining, weather conditions. In the summer, more people are walking and fewer are driving, et cetera. And so you might want to, in the transportation area, we've extensively used digital twins to simulate the physical environment, the urban landscape, for example, and then build algorithms of what's an efficient routing process. So now let's go, get the right button here. So where's the supply chain case in all this? Sort of summarizing what I've said in some sense, digital twins create value when A, there's uncertainty, which is the environment we all live in. We're optimizing over many variables, as we'll talk about in a bit. We have, on the one hand, access to high-resolution data. On the other hand, the data is incomplete. So our optimization problem is we have, for those of you in the procurement side of supply chain, oil prices have gone down in the past week by about, 10%? Since 2002, we've seen increases of anywhere between up 100%, down 30% in oil prices. But even in very short term, we've seen variations. So different gasoline prices might lead to, and different energy prices might lead to different transportation modes. At what point do you go from truck to freight? We also saw from truck to train, we saw trucking prices go up many percentages a couple of years ago and then come back down after COVID again. So how does that's just one aspect of your, so do you use rail or trucking, and what size trucking, and what types of vendors do you use in trucking? Well, if I'm going to use freight, then I get into the question of my warehouse location. Where do I place warehouses, and how do I expand on my warehouses that I've got? And so that leads to, if I'm going to use different warehouses, how do I utilize my vendors, right? So how does changes in transportation costs impact warehouses, but it could also impact my choice of vendors and how much I want to manufacture, and using different vendors in my vendor network. And then add to that an international aspect through international shipping costs that have changed with the issues going through the Suez Canal, maybe political issues about using different international vendors, obviously exchange rates, and you now have a very large-scale, multivariable optimization problem that you can try to solve. The traditional way is let's solve this once and hope we got it right, and hopefully it'll be correct for the rest of eternity. The better way, which I'm recommending, is use a digital twin. Simulate the environments. Some of these you can develop algorithms for when to go from one mode to another, especially if the different modes are easy to change. Some of these are more one-off changes when you see a certain environmental change, like shipping costs have gone up tremendously. Let's solve that problem. Access to high-resolution data is sort of obvious. The question is, how complete is that data, right? But we have IoT data, we have ERP data, we have CRM data, we have our vendors' ERP data, we have some of the companies that we've worked with even had multiple ERP systems, and they gave us a lot of data, but some of that data is incomplete. We don't have a complete mapping, even though we do have IoT. So that's sort of the supply chain part of the argument of building the digital twin. Where's the AI of it? Because I said, well, you have to show an AI story too. So AI has two ways that it contributes a lot to this discussion. One is especially for those of us who are digital adopters and sort of getting into still learning this, we have many disparate data sources. Sort of one source of data that we have is just contracts, right? Our vendors have contracted, told us that we can do a lot of things. How well we execute those contracts to our benefit is questionable. We have invoices, we have orders, we have customer orders, we have customer forecasts. Not all of these are always given in the same language, time, units, currencies, etc. We have data that comes in on spreadsheets. We have data that we've collected on spreadsheets, PDFs. We have, as I said, multiple ERP systems. And so AI is actually very good at collecting all of this data and interpreting it and trying to make sense out of it, right? Large language models, that is their contribution, is taking this and filling in those gaps. What do the disparate data systems actually mean? Some of it might be, as I said, very high resolution. Some of it are low resolution, like a contract or an invoice is not very high resolution. But we can now we can ingest at least all of this data to start making sense out of it. Number two, AI can actually help build the digital twin. First of all, it can say, okay, we have a lot of data. This is a lot of the data that I can make sense out of. But there are still gaps in the data. They can analyze, as I said, the various, the disparate and various data sources and make sense out of them. We can build now models to forecast how certain actions and certain environmental changes will have an impact on sales, on customers, on vendors, on how will different shipping methods and price increases through, say, shipping methods have an impact on demand, so we can use the AI or the machine learning components in the forecasting of sort of smaller scale, smaller scale questions. And then, once we build the digital twin through traditional methods and AI, and we won't get to the resolution that the engineers get to of having every package being mapped throughout the entire system from cradle to customer. That's not the resolution that we will get to, but we will be able to have a somewhat lower resolution model of our environment. AI plays a role in the evaluation or the actual running of the digital twin. First of all, AI is very good at ideation, coming up with scenarios. We like to focus on the scenarios that we are familiar with, and AI can think outside of the box. Here's what competitors have seen, this is what others have seen, this is what's been presented in sci-fi. Some of that scenario ideation can be brought to bear on actually evaluating different scenarios and what might happen in the environment. Because if I can think of many different things in the environment, I can now create better solutions to that. And then we can use generative AI, right? So in this environment, we can evaluate the simulations and do some sort of robust optimization, right? What sort of optimal solutions would we have that would be effective against, or many different scenarios or several scenarios, and so we can now expand, and we can utilize generative AI to promote, to actually give us recommendations through, as I mentioned earlier, the large-scale multivariable optimization problem with tremendous uncertainty. The direction this goes is solving two very different, or developing two very different directions. One is algorithmic solutions, right? So as we see small changes in gasoline prices, we can then, and warehousing costs, we can be more effective at utilizing, making those changes, and we can make those changes in an almost automated fashion, depending on the contracts we have with vendors, or depending on the space we have, et cetera, but we can make those sort of automated changes, increasing the efficiency of supply chain management a few more percentages. And then we could have what I call single case solutions. We have disaster recovery. We want to build out a new network of vendors. We're considering adding a vendor to our portfolio. We can, we could bring in that vendor into our simulation or a digital twin and figure out the value of that additional vendor sort of in a one-off optimization problem. So just to summarize, McKinsey came out with this slide as well, and at least the title says that supply chain management has shown the greatest revenue increases. Already from the use of generative AI. As I said earlier, generative AI is going to be required of you and I in the near future. I've given you one response to that requirement is let's build digital twins so that the digital adopters can catch up to the digital natives.